26 years. Okay. So I've been associated with this product since its inception. Now we will start a brief introduction about the software, and then we'll go directly to the demo of the software. So I will share my screen and let me know if you are able to see my screen. Okay. You're able to see my screen?
Yes, madam. Before starting, I will introduce our institute, madam. Then we will
Sure,
start it.
sure.
Within
Yeah.
2 minutes, I will introduce.
Yeah, please, please.
Good evening, madam. This is Dr. R.M. Patil as an associate professor in electrical engineering department. Along with my head of the department, Dr. Balchandra Godbole sir is also there, and other faculties also there. Our institute is located in Maharashtra, SKN Sinhagad College of Engineering, Korti, Pandharpur, which is the holy place of Maharashtra, where
Yeah,
we
yeah.
are having 5 branches, that is electrical, civil, mechanical, ENTC and computer science. So overall strength of our institute is near about 5 to 8,000 students are there in the campus. We are having a good campus and that much. So I will not take much time. You can start your session, madam. Please.
Okay. Thank you for the introduction. Um, Thank you for giving an opportunity to showcase our product. So I'll start off with the presentation.
Yes, madam.
So in today's session or in the discussion, we'll be looking at into My Power. That is the flagship product of PRDC. PRDC is Power Research and Development Consultants. We are into development consultancy related to all power system issues and power system community from the past. From 1994, that is almost 28 years, 28, 29 years. So we are into this field, and MyPower is one of the flagship product of PRDC. It is a Windows based software which is used for simulation studies. It is used both at the at various levels of power system operation, that is planning, operation, and also like to solve many of the unsolved issues in the community, like power system related operations, and also like at various stages for design, operation, and also the planning. So I'll be introducing you to the various modules that is available in MyPower. This is a offline like power system simulation software. So I'll just tell you about the overview. What are the modules that are available? More than 50 modules or applications are available as part of this MyPower, but mainly I'll focus more on the generally used softwares like load flow, short circuit, stability, coordination, protection related activities, harmonics, and so on. Then we'll go through what is MyPower, then what are the modules that are available in MyPower, and what are the various kinds of studies that can be done, and the kind of simulations that can be done using the software. And then I'll take a simple example, and then we can do various studies for them. Sir, how much time? Now it is 3:40.
One
So
and a half hour, madam. 1.5 hour.
okay, so fine. Till I have time till almost we'll take up till 4:45. We'll do this one, and then maybe we'll take up some of queries
Okay,
or
madam.
questions if you have.
Okay.
Okay. So my power, it was started way
Uh,
back. Yeah.
Madam, you have shared the slides till no, na?
No, no, no. I have shared only
Okay.
the brochures.
Okay.
After this, I will share
The
the.
presentation, have you shared? There is no,
No,
we are
sir.
not able to see your presentation.
You are not able to see.
No,
Just
madam. Please.
Just let me know if you are able to see. You're able to see my screen?
Yes, yes. Now it is visible, madam.
Okay, fine. So in the beginning, I was showing you this will be the agenda of what we will be looking at today. That is MyPower overview. MyPower is the product name. So then, what are the modules that are available, and the MyPower as a platform, and then we'll go for the demo. So, MyPower, it consists of, it's a suite of like various modules. So all the power system simulation studies, what you need to do is available in MyPower. So it can be used both for transmission studies and also the distribution studies. And there is an offshoot of this, like you have the protection setting calculation tool where you use the fundamentally for doing the protection setting calculations. So as a different flavors of MyPower, we have MyPDAP, that is distribution analysis package, and then this is used for transmission analysis, and also like power system setting calculation tool where the focus is more into the protection calculation, both the graded protection and also the individual protections. So those are the different flavors of MyPower. MyPower is basically used by all leading distribution and utility companies. They use it for their planning. Then we have as a part of this, you have the forecasting also. Hello,
Yes,
hello.
yes.
Yeah.
All of you, please mute your mics. All students, please mute your mic.
Okay.
Okay,
Thank
madam.
you.
You continue, madam.
Yeah. So this is used by all utility companies. The if you name any of the transmission companies in India, so most of them, all of them are using this package. Like if you say Karnataka KPTCL is using, when it comes to Maharashtra, MSCTCL is our client, and like all the Tamil Nadu, Kerala, like all the electricity boards, transmission companies use our products. So here the main advantages, as I told you, it can be used for both transmission and also the distribution companies. So they are our main clients. They are our clients, and then the consultants who do consultancy studies for these utilities or the industrial uh, like organization, so they'll also use the software for doing various studies. The industries like Reliance, Adani, they are also our customers. They use the software for doing various studies. And also like one segment what we have is the academics also. So in many of the cases, like at least in Karnataka and in some of the universities in Andhra, so MyPower is made as a as a part of the syllabus in the for the power system labs. So using the software, so it is a toned down version. So see, we have done analysis say from two bus system, like for analysis of small textbook problems, up to around 1 lakh bus system, where bus in the sense that the nodes system where we represent the whole of India, or at certain voltage level, or at the state level, the complete states or the southern region. So there it comes, the number of buses comes to around 1 lakh buses. So the software is used from 2 bus up to 1 lakh bus system. So we do a lot of analysis using the same software. So our clients include, as I told, the sectors are like the utility sectors, the transmission companies, the distribution sector, the SCOMs, and then the academics, and also like the consultants. So these are our major client sectors. So they use it for the, as I told you, both for design, operation, and also for the planning of the studies, planning of their system. So here, when I talk about my power, it has got. See, now I told the number of buses from 2 bus to the 1 lakh bus system. Now, when we are analyzing the power system, so there are different kind of studies. You have the steady state analysis, the transient, and also the electromagnetic transient. So there are some studies which is the snapshot, like that particular instant, what is the like system you will be observing, and there is a time based, where you observe the system over a period of time. Like when you talk about transient stability, basically it will be in a few milliseconds, or in some cases when you're doing islanding studies and all, it may go up to say 10 seconds. So there you're observing the system at different intervals of the time, so you can be performing the transient studies using the software. And also when it comes to the electromagnetic transients, like arcing flash or magnetizing inrush current, or you want to observe the system during the transient. So we have a module for doing such kind of analysis, that is electromagnetic transient analysis. So there you'll be observing the system in microseconds. So your time interval for observation will be in that. And also nanoseconds also, like search arrest studies or power search studies. So this software can be used for performing studies from nanoseconds to when it comes to your forecasting, it will be in terms of years, like short term forecasting, long term forecasting. The same software we are using it for forecasting for like 5-year plan or 10-year plan, the expansion plans. So all those analysis can be done using the software. So from nanoseconds up to years, whatever the analysis which falls in power system, you'll be able to do it using the software. So here, as I was telling, I'll go to the next part. MindPower as a platform, you have the various time analysis which I was talking about. So here, I've classified here like power system analysis and steady state, then the dynamics, then you have the protection, forecasting, and also like network modeling. So this classification is just for what are the different ways or different analysis that can be performed. So if you're doing any analysis, first is you need to model the system. So there are various ways of modeling. I'll show you the what are the kinds of networks you can generate. Then you have the centralized database. That is, once you make the database, you can perform the various analysis. So that is on the network modeling. We have a single line diagram generator, like using which you can create various single line diagrams. And I'll be showing like what are the kinds of single line diagrams you can generate. And then like if you have the data in other formats, see in case of small systems you can always draw it, but if you already have the data in a particular, in a different format, that data also can be imported, and you can straight away start doing the network. For example, when we talk about all India network, so the POSOCO, they give the raw files. So that is a one interface file kind of thing. So that like the all India network can be built, say in just few seconds, few clicks, you'll be able to get a complete network of the whatever the files that is available. So that is what I talk about when I say interfaces. So we can import directly from the raw files, that is a PSSE output generated files, and then IEEE, GPS, SCADA, and also from the AutoCAD. So the first limb, what you see is the network modeling, and this is from the scratch. If you want to do, you can use the software and do it. Otherwise, if you have the data in a different format, so we have interfaces for importing that and creating the network. So now coming to the first part, that is the steady state analysis. Now I'm just introducing what are the different analysis that can be performed. So as I was talking about, like from nanosecond up to number of years, we can do the time span. So first is the steady state analysis, wherein you don't have, or you don't model the variations of the system parameters. So we have this load flow. So I think all are from power system background, you know what is the load flow. So here, in case of my power, load flow is not just generation load balance. We have other options also included as part of this. What I mean by other option is you have real power optimization, reactive power compensation, and then DC load flow. So when I'm showing the software, I'll show you like there are so many features that are included as part of the load flow, because load flow is the fundamental study, the first study what you do before you perform any other analysis. So then you have the short circuit. So you have in this short circuit study, it depends on what is your objective. Like when you go for a steady state short circuit, when it is transient or when it is electromagnetic transient. So all the three modules will have this short circuit studies, but what study you do depends upon what is your objective. Okay, so if I want to just check whether my breaker ratings are sufficient, then I don't go for electromagnetic transient analysis. For me, steady state short circuit is sufficient. So when I'm checking for the, for example, doing a critical clearing time, so then my steady state fault analysis will not be of much help. So whatever analysis, see, these are all the components like load flow, short circuit, or whatever the analysis. But all these studies, what you do is going to help you to solve some of your power system related issues. So the software is not going to tell you which study you have to use. So your problem statement, like what problem you're trying to solve, that has to be very clear. And we have to define what is the solution for that. So you have, see, for example, if my problem statement is my relay is inadvertent. Second, there is some disturbance. Hello. Yeah. We have to convert the problem statement into series of analysis what has to be done. So always the software gives you a tool to arrive at the solution. So as a power system engineer, we should know what is the problem and what is the solution. See, the software as such will not give you, okay, you do load flow, then you do protection, or you do load flow and then do a transient stability. So these are the steps that we as a power system people have to deduce, like what are the studies that has to be done. Say for example, if I'm doing a magnetizing inrush current studies, so that will be my problem statement. So my solution will be I have to do a electromagnetic transient analysis, because I cannot do a line charging or charging using a transient stability. So if we do, if we see any of the software packages or any analysis, most of the studies what we do will be in the RMS domain. So we'll be using the RMS values while doing the analysis, except for the electromagnetic transit, where all the values are the instantaneous values, which will be when we are doing the analysis, that is what will be considered. So coming back to our steady state analysis, you have load flow, short circuit. Normally for a transmission system, you use we assume that the system is balanced and go for the normal single phase equivalent load flow. But when it comes to a distribution level, so there cannot make an assumption that it is balanced. So you go for the three phase load flow or the unbalanced load flow. So as I told you, what study you do depends on who are your audience, what is your problem, and what is you're trying to solve. Then you have this time series load flow. That is again why I put it as study status, like based on your meter data, like 15 minutes or half an hour meter data. Then you can do that based on the load curve. You can do the analysis, find out what is your monthly loss, overall annual loss, and those kind of analysis can be done. So three phase load flow and normally time series load flow, use it in the distribution system. Then is observability and state estimation. So this is again like when we are doing the SCADA and you have the meter data, and whether that system is observable or not, where the meters are placed, whether if meter is placed at one location, whether you'll be able to estimate what is the flow in the other lane. So these kind of like bad data estimation, those kind of analysis also can be done. Next is the harmonic analysis. So these are all we have put under the steady state analysis. See, when you open the software and see, you will not get a classification list like this, but to understand better and to put in the proper perspective, I've just put it in different heads here. So harmonic analysis, as you all know, there are so many harmonic sources in the system. So when an industry or when somebody connects to the grid, so there is a limitation, like how much they can inject to the grid, because otherwise you will have a lot of other issues like flickering and also at the point of common coupling, there is a fixed harmonics which is allowed. So if it is beyond that, the total harmonic distortion, if it is beyond a certain value, so there is a policy, there is a penalty to be paid. So during such situations, the industries, they do this harmonic analysis where they place wherever the harmonic sources are there, and you do analysis. One is the measured value, and then the analyzed value, what is the total harmonics distortion. So those kind of analysis also can be done. That is part of the harmonic studies. And also, like when there is a harmonics that is introduced, how do you reduce that one? So you have your filter design, and when you put that into the system, how it is going to reduce your distortions, those kind of analysis can be done. So coming to the power system dynamics, like when there is a, like you're observing the system over a period of time, so you have this transient stability, dynamic stability, then you have this subsynchronous resonance. And also, like see, you have when I talk about transient stability, I think most of you are aware what it is. So there will be a major disturbances in the system. If there is a major disturbance, how your system is going, if I have to tell it in simple terms, a disturbance, and then how your system is going to behave during disturbance, and then when the fault is cleared, how it is going to come back to the normal condition. So during this period, there are various equipments or elements that are going to come into picture. Like you have your, for example, if there is a disturbance, your AVRs, the automatic voltage regulators, your governors, and then maybe like SVC, all those things are going to play a part to bring back the system to normalcy. So if it fails, it goes to, I mean, the system will collapse. Like that analysis kind of, whether your control blocks or your system is proper, uh, whether for after a major disturbance, whether it is going to come back, or what is the critical clearing time of the generator. So you want to see how much it can withstand, after which it is going to collapse. So these kind system, ಮುಕುಂದ್ ನಾನು ಡೆಮೋಲಿ ಇದ್ದೀನಿ ಮುಕುಂದ್. I'm so whether your system is going to come back to normal, or what are the changes that has to be done, or if you want to design a control system, how it can be done. So those kind of analysis can be done. So this transient stability and the control blocks, this control blocks is basically your design of your transfer functions, and that you can put it in the system and then verify like how it behaves. Next is the dynamic stability. So these eigenvalues and eigenvectors. So those kind of analysis can be done. Like for small changes in the say your AVR reference or governor reference, if there is a change, so how the system is going to behave, those kind of analysis can be done. Then the subsynchronous resonance. Now coming to the power system protection, this is the brief classification of this. You have this graded protection and also the unit protection. So some of you might have been aware, like in 2012 or 13, there was a major collapse in the northern grid, like whole of North India was in dark. Okay, so that happened, right? After that, there was lot of analysis that went to it, and our team was also part of that in analyzing why that happened and how to avoid that in future. So during all these things, there were so many recommendations that has come up. So we have included, or we have aligned some of the features to meet those requirements. We have separate products also for that, but the fundamental setting calculation tool is from MyPower. So you have general philosophies for how the distance relays has. I'm just telling an example how the distance relays has to be set. What should be the like percentage, like your philosophies. All those things can be modeled. So overcurrent and distance. So these are the graded protection where the system parameters are going to play a role, and the others are the unit protections. Like all most of the unit protections, whatever is there in the field, can be modeled in MyPower. So once you do the settings, then you're going to verify the settings. That is the protection simulation. Like you create a fault in the system and see how the relays are going to operate in what sequence. Next is the DR file analysis. This DR is the disturbance recorder file analysis. So there is a possibility like you get the disturbance recorder file from the system, so you can play back that one and see like how the relay is going to behave for that. So that analysis also can be done. So next is the forecasting. You have the long term forecasting and the other interfaces. So this is in a nutshell like what MyPower can do. So this will be the main launching screen, or like where you start off with doing the various studies. So when I go to the software, I will show you what are the things that can be done. So here basically you model the network. So the procedure is like this: you model the network, and it is a, as I told you, it's a centralized database. Once you model the network and the database, you can perform various analysis. So the first thing what you do whenever you're performing any analysis is you build a network, right? So that is what I was showing in the beginning. One is you draw it from the scratch, and then, or if you already have some data, so that has to be converted. So this is the sample single line diagram. So I'll show you how to draw that also, but this is a snapshot of that. So on the right hand side, whatever you see or the various symbols that can be drawn. So here, like some of the things are related to the database. There has to be a database, and some are just symbols here. So you can see here, because you're all from power system, you know what this single line diagram means. So you see your generator here, then you have the buses. These are the red, green, and all that. So you have the voltage configuration. So each utility may have a color codification for the voltage levels. So that can be configured. Say like 11 kV is red or 220 kV is green. So that configuration can be done. And for visualization, you can even have the vary the thickness of the bus to identify what is the voltage level. And then you have this is a sample network where you have all the relays placed. You have the transformers, and then you see here like a grid. This is a grid, and here the transformer representation. So the first step in analyzing any of the network is creation of the single line diagram along with the database. So in my power, you have various ways of creating the single line diagram. So this single line diagram, what you're seeing, I think you're very familiar, like in your textbooks or when you like you're given a problem, everything will be given in this format. You have a generator representation, and then you have the lines. So like this is how it looks normally, even in your textbooks or whatever the analysis you do. Okay. So that is one way of representation of the system. So here, if you see, so in MyPower, you can create the networks of this complexity as well. So if I zoom in, like actually I put it in a PPT. Otherwise, like if I click on any of the lines, it will go to the corresponding data. So on the left hand side, what this is a geographical representation of the system. On the right side, what you see is a complete southern region network, and on the left side, what you see is a zoomed version of the Karnataka state. So this is also possible, and this is actually a live network. What I mean by live network is for one of the studies they have created this kind of network. So with the same software, you'll be able to create a network, a simple network, also a geographical network. Okay, so this is one more way of representation of the. This is similar to what I showed in the first slide. So this is also one of the industrial system network. Okay, so next, this also can be created. I mean, the typical distribution network, so where you have the here, this is actually drawn by hand, like somebody using the coordinates they have. I mean, our team has drawn this for one of the projects. So this is a distribution network, and here you have the GPS based distribution feeder network also can be drawn. So here, you must have heard like they do a GPS survey, like where the poles are there, what is the walkthrough surveys they do, and they collect the data. So once the data comes in, that can be converted into this format. So this is a GPS based feeder. See, the first single line diagram, what you do, it's like for electrical network analysis, that is sufficient. But actually, when you're doing a distribution system where you want to know where you have to put the substation, or the new consumer where he is, and from the feeding point up to that consumer point, if you have to take a service line, so what are the impact of that? So if you have to do those kind of analysis, like we use this GPS based distribution network. So these kind of diagrams can be generated using the software. And there is one more block schematic representation. Here, this is also one form of representing the network. So if you have a very large network, so you're not going to do individually for each of the substations, you will have an overall network. And then when you click on any of these boxes, you see whatever the red box. This is also actually one of the projects what we had done for Karama, that is the Qatar electricity supply company. So here, so these are the substation representation. What is the connectivity? So you can see Alibat or some names like Middle East names. So when I double click on this blocks, so it opens up the single line diagram of the corresponding substation. So these kind of networks also can be drawn. Okay. So I'll not go into the network viewer. So the first step, as I was telling you, is building of the network. Now, once the network and along with that the database is built, you can do perform various analysis. So we'll go whenever I'm showing the software, I'll be showing it. So here, the same network what I showed in the beginning. So here the results of load flow is plotted on the single line diagram. Again, when the results are plotted, you can define like whether it is the flow is within the range or it has exceeded some percentage. So those kind of color codification is there for even for the results. And when we are seeing the software, when you're plotting the results, you can even see the blinking of the text wherever the fault level, wherever the flow level is exceeded. So this is one of the diagram where you have the flows. You can see like what is the generation, what is the flow in the transformer, what is the transformer tap. So these kind of things, the visual representation of that on the single line diagram. Next is, this is a fault analysis. So once you set up the system, you can create fault at any point in the network. Even on the single line diagram, you can see a fault symbol at B4, like that's a 220 kV bus. So you can see a fault symbol. So if the fault is occurring at that point, so you can see like there is a fault symbol. You just pick that symbol and put it on a bus or on a line and say what percentage you want to create the fault, the type of fault, like whether it is three phase, single line to ground fault, or double line to ground fault. So you choose the fault type. So then you get the a visualization like this, where it shows what is the flows in different parts of the system. So when I'm showing fault calculation, I mean short circuit study, I'll also show you. One is you create a fault on the bus and it is going to give for that condition what is the flows. The other one is, many of the times what happens is, you know what is the fault current. The fault current is known. So I can tell, okay, at this bus, this is the fault current. Now show me the flows in the other part of the network. So those kind of, you limit the fault level to whatever the measured value, and then see how the distribution is there, or whether any of your breakers have exceeded. So those kind of analysis also can be done. So stability studies, as I told you, it's time based, so you can get various graphs. So the other short circuit and load flow, it is a yeah, like for that instant what is the results. But when it comes to stability, it will be from say a few milliseconds or seconds you are going to observe the system. Next is the relay coordination. So this is again, I've used the same sample just to show the different studies. So here you can see 51, 51, 80, 70. These are all the standard codes for the relays. 51 is a overcurrent relay. 80, 70 is a transformer differential relay. So all these kind of relays can be modeled, and you can see the CTs, everything will be modeled. So once the system does the coordination and gives the settings, the activity or the final decision would be like whether verification has to be done, whether the settings are proper or not, whether you need to change any settings. So that time you can create fault at different buses and see the sequence of operation. So once the coordination studies are done, you'll get a graph like this. And even in the graph also, once you see the graph, if you're not happy with the results, see the results will come based on what data you are given and what is the philosophy that has been used, what is the characteristics and all those things. So if you're not happy with the results, you can always move the curves and see the curves are going to move within certain range, like based on the plug setting and the time multiplier settings. Next is this is a simulation what I was talking about. You can create. There is one very good feature in MyPower that is called as protection simulation. So whenever you are doing the settings, normally when we do the settings, what we do for overcurrent relay settings, distance relay settings, and also do all the unit protection settings. So once all the settings are done, now a consolidation of, I mean, how the system is going to behave or how the relays are going to operate. When all the settings are done, you have set the settings, and now you want to see whether my transformer differential is going to operate, distance is going to operate, or overcurrent relay is going. So when we do protection simulation, you are going to create fault in the system, and all the relays which are placed in the uh, network is going to respond to that, whether it operates or doesn't operate. So if it is picked up, you can see here there is a red, like it is encirculated by a red circle. So wherever the red circle is there, it means that the relay has picked up, so it has sensed the fault. And the first relay whichever is operated starts blinking, and then you can always see the sequence of operations. Then the electromagnetic transient analysis. This is what I was telling. It is a like instantaneous values. So if you see the graph, it will look something like this. So in all other graphs, transient stability, it will be kind of a straight line. As I told you, it's all RMS values. So we have different studies that can be done in the electromagnetic transient analysis. The line energization, magnetizing inrush current, how it happens, and also like if you have the motor starting, arc flash, those kind of analysis can be done. So this is how one of the results of that. Then you have, when it comes to the power quality, you have the harmonic analysis. So I was talking about that, like the THDs and how you're going to reduce that. Those kind of analysis can be done. So next is the forecasting. So you give depending on the historical data, we have different methods for forecasting. So this is like you get in the graph and also in your visualization what is the forecasted values and the actual values, whatever is available. So this is basically, there is nothing much power system in this. It is basically a statistical analysis based on the historical data and also the various methods of forecasting. The values will be forecasted. But for planning analysis, this will be your input based on what is forecasted for next couple of years. Then my generation planning and transmission planning has to be done. So this load forecasting is going to give you an input or indication of what has to be the other planning that has to be done for generation and also the transmission. So these are the various options you have for doing the load forecasting. And also the other advantages, like you can model the renewable energy sources. You have the solar modeling and wind modeling, and currently we are working on biomass and other renewable energy sources. As of now, we have the solar and also the inverters and wind generators. So the effect of that in normal load flow, and also uh, transient stability and short circuit studies, the effect of that can be seen. So this is a small presentation on this. Now we'll go directly to the software. So any questions? Hello?
Madam, one question is there. If
Yeah, tell me.
because since we are using MATLAB here for the
Mm,
programming of the whatever the stability, load flow analysis, and everything.
mm,
If we have done the program in the MATLAB, it can be
mm.
converted into my power software.
Sir, my power is for example, if you have done some analysis, you have done a load flow using MATLAB. I'm just telling an example.
Okay,
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 so you have created a function or you have done it in MATLAB. So my power is already having load flow analysis with various methods. Now,
okay.
what you are asking is whether you can do load flow from that and plot the results, something like that.
Yes, yes, madam.
Yeah, that see, my power takes input and output in a particular format.
Okay,
Okay, so you want to do, you want to call your program for doing the analysis and seeing the results on the network. Yes, there has to be some tweaking or something has to be done from our end to give that interface, but it is possible like you can plug in the complete modules, but
okay,
not like it will not be an integral part of this, but it is possible to call your functions in this.
okay, 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 madam. Okay, thank you. Any questions, students?
Any questions? We will go next for the demo of the software.
Yes, madam. Yes, yes.
Just a minute. You're able to see my screen? Hello?
Yes, madam. Yes.
Okay, okay.
We are able.
So this is I've launched my power here. So these are the various modules. I'll just see how fast, how quickly we can see the various modules. So the first one is the power system network editor. So this is what I was showing you, like how you can create different kinds of network. The single line diagram, geographic based, then GPS coordinate based, or just a block diagram. So these kind of the networks can be created using the network editor. Next is the database manager, so where the actual data resides, the all the power system related network data. Next is the free programmable blocks, that is the control blocks. Basically, like you can create various transfer functions or the control block. Say for example, if you want to model a different kind of AVR or a governor or a SVC or transformer load control, so those kind of models can be done and you can attach that models to the main, like you have, if you have created a generator, so you can attach, say you create a control block and then you can attach to the generator and see the performance of your AVR, how it behaves. So those kind of transfer functions can be built using the free programmable blocks. Next is the comprehend viewer. It is the basically the disturbance recorder files that can be opened, the different formats of comprehend file. So this is used, as I was telling you, the DR file analysis, the disturbance recorder analysis. Based on the waveforms, it is going to tell what is the type of fault, what is the fault location, and those kind of things. And then you have the line and cable parameter calculation. This is based on the tower configurations and the cable configurations. It is going to estimate what is the resistance reactance for the given configuration, given conductor type. So this is the long term load forecasting. And then you have the ground grid design, DC network solution, and also the battery sizing. So these are all the major modules. That is a user interface module. Then you have the graph utility, that is like whatever the analysis is done. So it generates graphs if it is a time-based analysis. So to view those graphs, these are all individual modules here. But when I get into the software, so if graphs are generated, a corresponding icon will come, so I can directly use the graph utility. So this batch mode interface is basically to import the data from third-party software. Then you have the automatic single line diagram generation. So whatever the networks you had seen, like the single line diagram, so the user can draw that one. I mean, whoever is the want to draw it, you can draw, or you can directly create it. It's so flexible. Like you don't want to draw the single line diagram, but still you need to do the analysis. So that is possible where you're going to tell the system or the in the database you're going to mention from which what are your voltage configurations and how many you are going to create the buses and also the connectivity information. So from there directly you can do the analysis. So SLD or the single line diagram is not mandatory for performing any of the analysis. You can directly use the database editor and do the analysis. So once you do that one, if you want to do this automatic single line diagram generation, is basically based on the connectivity information that is going to generate the single line diagrams. Next is this is for exporting of your data in AutoCAD. I mean the results and also the network information. And then you have the studies. So MyPower provides you with analyzing the system at various levels. One is using the single line diagram and the database. Next is you can do only using the database, and at other levels like there is you can write or you can enter the values in a text and directly use those text also to perform the studies. So these are the flexibilities. Next is the tools. So these are all some small the utilities or the programs which is like it doesn't require much of the system data. For example, you have this present worth analysis. So this is basically a financial analysis where you give what is the investment, what is the rate of interest, and those kind of things. And based on the life period of the project, it will tell whether it is beneficial or not. So these kind of small studies, you have a unit commitment, critical clearing time, then the differential equation solution. These are all some small like y bus z bus formation. See, when we are doing the analysis internally, we generate the y bus z bus formation, and you can view it also in the detailed print. But some of the cases, what happens, these tools were basically developed for academic like for the students. Sometimes like when you have to do a load flow analysis, now you don't have to go through all those single line diagram and then draw the network database, create the database. So if you want to quickly do the analysis, if you have the connectivity information and the basic data what is required for doing a load flow, you can directly do the analysis here. So this third section of tools is basically for the students. Yeah. So this is the different modules. Now I'll go to the power system network editor directly. Directly in the sense I'm going to open whatever the samples I had shown. So here on the right hand side, you can see there are various symbols. Now I'll just draw one generator, one transformer and a load. So you'll just see. So first, as I told you, I want to configure a database. So you can do it independently or along with the database. So I'll just take a simple sample one. I'm going to name the database. And then say connect. So this is a normal way of creation of the single line diagram, but you can, as I told you, there are other ways also. And then whether here the general information, so where the database will be there, what is the network name. So then the voltage configuration. This is what I was telling, like you can in your system, whatever the voltage levels are there, you're going to configure that. And then what is your base MVA, base frequency. And also, like, you can give the data in per unit true, means you're giving the data all on 100 MVA base. If it is false, everything will be on its own rating, and for lines it will be ohms per kilometer per circuit. So these are, and if you're doing some financial analysis, like capacitor placement or real power optimization, so there will be currency which is going to come in your report. So what is the currency you want to put? So if I'm doing it for Indian client, I'm going to put it as rupees. So if I don't put anything, it will by default take it as rs rupees. But specifically you want to say you're doing for a Singapore client, so it has to be SGD or Hong Kong dollars or whatever the currency, or Qatar if you're doing it maybe dirhams or dinars, whatever. So that currency you can put here. So here in your report it is going to show this currency. So now I'm going to leave it as it is. Okay. So now I'm just creating a framework for my network. Okay. So it is just updating some libraries. Okay. So I want this to close before I start my network drawing. Okay. So now this is my canvas. Here I can draw the network. See, whenever I'm drawing any single line diagram, as I told you, I'm going to configure what is the color. This is a color codification. So here you can see what is the colors for this. Okay. So I'm going to retain as it is. I'm not going to change anything. And this is the bus width I was talking about. Now on the right hand side, I have a symbols here. So now I'm going to draw one 11 kV bus. So I've selected 11 kV here. So this is a 11 kV bus. So it is going to ask me what is the bus number and name. So this is the database. So here the bus here in case of my power. So bus is a fundamental connecting node, bus or substation. We call it as a bus. So that is at least one bus has to be there. Say there are different types of elements. You have a series element and a shunt element. So if I have to put a shunt element, there has to be at least one bus. So the shunt has to be connected to a bus. And if it is a series element, it has to have minimum two. So this is a 11 kV bus. Next is I'm going to draw 220 kV bus here. So I have selected 220 kV. So I'm going to draw 220 kV bus. Okay. So now here I want to draw one generator. So I'll go to the generator. So it's going to be like it's a shunt element, and it is going to ask me for one connection. So this is a generator. So here the concept here is you have elements and the library. So you have both manufacturer data and also the field data. So the field data is like what is actually there in the system, like the connections. Library data is like a manufacturer details. So same kind of transformer, maybe I mean generator or transformer, maybe at multiple locations. So in the library, I'll have only one entry, but in case of the elements, I'll have, like if there are two generators, I'll have two generators. So this is the generator data here. So you have the bus number, it automatically comes based on that connection. Then you have units in parallel, and this is the manufacturer I was talking about. So here in the generator library, you're going to tell what is the voltage level, megawatt rating, and then all your parameters of R, X, XD dash, XQ dash, XQ dash. This is the modeling. All the part of that you're going to specify here. This is basically the manufacturer details. And also like whether it is star grounded, and if you have any mass details. So the level of data that is required depends on what kind of study you're doing. So if it is only a load flow analysis, this armature resistance, reactance, all those things will not have any impact on the studies. So depending on the study, you can enter the data. So I've added one generator here. Okay. So next I'll go for the transformer. So transformer is a series element. So see, you can here I have to place a transformer here. It is going to I have to connect to a from bus. So as soon as I go near the bus, it is going to highlight that. So I have to double click on that, and then it is asking me for the two bus. So this is the transformer. Similarly, this is the transformer data, and then you will have the library, corresponding library. Okay. I'm just drawing quickly. If you want anything in particular, you can stop me. So this is the transformer. Okay, this is the transformer library. So for any element, we'll have a for any equipment, we'll have an element and also the manufacturer details. Okay. So I've just added one transformer, and then now maybe I'll add a load. So then I have to give what is the load. Yeah. So I can enter the real power megawatt, reactive power, and also the power factor. So this is like a detailed one. Like because I'm just giving you a demo, I'm not going into the details of that. But this is how you model the or create the single line diagram. Now I've created this diagram. Now I have a generator, transformer, and a load. So you can see here some ZZ codes, right? So these ZZ codes are the placeholders. Like it's like a variables. Like once the analysis is done, where the results are going to be plotted. So now I have created this single line diagram. So the procedure for creation of single line diagram, if you're doing from the scratch, is like this. You create, you open, connect to a database. So new database will be created, and then you are going to draw the network. So once you draw the network, you go for the studies. So here I've gone for the low flow analysis. So here I'll quickly go through what are the options that are available. So as I was telling you when I was introducing to the load flow of my power, so there are various options available here. So it is not a simple generation load balance kind of study here. Okay. So what is the here? I'll just quickly tell you what it is. So techniques. You have Gauss-Seidel, Newton-Raphson, fast decoupled method. So what is that method you want to use? See, as you all know, like all methods will not solve all the cases, right? So there are some ill-conditioned systems or some systems where you don't have the proper data. So it is not that Gauss-Seidel will solve load flow for all the kinds of system. So there is some methods which are well suited for some kind of systems. So normally what we do is we use the FDLF, that is a fast decoupled load flow method. But in some of the cases that is going to fail. Okay, it is not going to give you a converged results. But when you see in an actual system, like in the field what you have, there is no system which is divergent. So convergence or divergence is only a terminology or a concept which is there in the simulation domain. In the actual field, there is nothing called as okay, my system is diverging. It cannot happen. So there is always a generation load balance. There could be so many other effects of that. Your frequency may be down or your frequency may be up because it is a frequency dependent also, your group characters. So there are so many other dynamics that is going to come into picture. So there is no divergent system in the field. So convergence or divergence or my number of iterations is everything is in the simulation domain. So like most of the cases, FDLF is going to, I mean, you get a converged results. But if you are not getting it, we can use the other methods. So default FDLF method. Now, the other one is the load flow type. So slack bus concept. So again, whenever we talk about slack bus, it is always, again, it is a simulation concept. Like there is nothing called as an infinite bus or a slack bus when it comes to the system. You can say like grid or connecting to the central grid or a grid with high inertia could be your slack bus. So when we are doing the analysis, there is nothing called, I mean, in the actual field, there is nothing like a slack bus or an infinite bus. That is again a concept of the analysis domain. So here, slack bus concept, if we use, so we assume that there is one infinite bus which can take or give whatever is required. Okay, so that time your frequency is maintained in the system. I mean, in the at least in the analysis, and it is always like the deficiency is given by that slack. Okay, so that is one concept of load flow analysis. Next is frequency dependent load flow. So frequency dependent is as I told you, there is no slack bus. I mean, everything has got a limit. So if that case is there, how much, like, what is a new frequency that is going to settle? So at least in Karnataka, most of the times our frequency is below the 50 hertz. So that is like all your group characteristics, your frequency dependent loads are going to uh, affect your frequency in such a way that it is going to be reduced. But in some of the states, I've seen the frequency is high because the load is low. So that is like, if you want to actually do a operational load flow, you have to go for the frequency dependent load flow. And here also you have different types of options. One is the flat island control and flat frequency control. So flat frequency control is you maintain the frequency, and then you see what is the additional thing that is required. Okay, flat tie line is you maintain the flows and then try to see what is the new frequency the system is going to settle. Then you have this optimal load flow. This is real power optimization, reactive power optimization. So you have your cost factors, generation cost factors, like C0, C1, which is directly, one is the capital cost, directly dependent on square of the power. So there are some formulas for that. So if you are given the cost factors, it is going to find out what is the right optimization studies will be done. So when it comes to Q optimization, so you have this what is the compensation, reactive power compensation that will be given to maintain your voltage. So those kind of analysis can be done. So the other one is the contingency analysis. Contingency is basically your changes in the system. Like I have a group of elements that is going on, or I'll define the, see, whenever planning studies or anything is done, they use the n minus one contingency. What it means is I have a system condition now. So if n minus one is one of the element goes out of service, what is the impact of that? So that we call it as n minus one contingency. So like that, you have n minus one, n minus two, but normally it is they stop at n minus two. What it means is parallelly two elements goes out of service. What is the impact of that? So that we call it as contingency. You can define group of elements that is going to go out of service. So it is going to tell which is the most severe contingency. That is, you have the contingency ranking analysis. See, basically, this contingency ranking analysis is used in the SCADA when you're doing the interface with the real time SCADA. So when that comes in, it is going to tell, okay, if these elements are going to go out of service, your system is very vulnerable or very sensitive. So this is usually the contingency ranking analysis, where you have the voltage and the flow ranking is used in the SCADA interface part. But as a part of the software, we also have it here. You can define the contingencies. Then is the B coefficient and economic dispatch. This is the one of the method. There are various other options. The interesting thing would be this, like tap option. So you can use for the transformer taps, whether you want to use whatever the user given nominal tap, or you optimize. Again, in the optimization, you can optimize the tap position. So use optimize all taps, or optimize only on road tap changer taps. So those kind of, these are the options. Next is slack bus. So here there is only one generator, so it is not showing me any option. Otherwise, it will show like you can choose the maximum generation versus the slack bus. So the program automatically chooses whichever is having the maximum generation, the scheduled power, or you can specify I want this particular generator to be used as a slack bus. So these are all the various options. Then you have P tolerance, Q tolerance, and number of iterations. See, by default, we would have given 15 iterations. Most of the cases, it will converge within that. Okay. So if not, we can change this one. Q check limit is the reactive power checking. So you know, in the generators, you have Q min and Q max. So in the initial stages, it will not be within that range. So after what iteration you want to check that Q limit. So that is what is this Q check limit. Then is load model voltages. See, normally we assume the loads to be constant power. But what happens if the voltage is varying or voltage falls below? It can never be constant power. It moves to constant impedance mode. So after what voltage level? So the model, the load has to become constant impedance. So these are the various options we have. So I'll go directly execute this. So now the execution has happened. Now this is a two bus system. This is what we have created now. So you can see here at what time it has converged, what is the voltage. So okay, you can see the results here. It has done the contingency analysis. I have not selected any contingencies. So here you can see what is the generation, what is the loads. Does not consider the okay. So the same thing, you can plot it. So like this, you can save this. Take the example. So this is a sample. Okay. So you can do once the once the data is given. So these are the various studies that can be performed. So here on the right side, you can see load flow, short circuit. Then you have this open access feasibility, ORCD, DRCD. So these are the different analysis that can be performed. So I'll go for short circuit study. I showed you the different options. So there is one more quick solve is there. So if the load flow is already, all the settings is already done, I mean, so you can just do it from here. You need not go to the like study information. And there is one more small thing which I would like to show. There is so now the load flow is done for this. Now if I want to do what if analysis, say for example, I want to open some of the things and see how there is a other option like where you fixedly open some of the things, you open the status of that. Then there is one more option called as dynamic simulation. So here, what happens is I can select any of the elements. Say I'm going to select this load and say open this load. So what happens? This load you can see here. This is open here, and then you can see what is the flows that has changed. Now I'm going to put back this. So this we call it as what if analysis. Okay. So now, for example, I'll open this line. So I can say element status open. I can even, if the number of circuits are more, I can even change that one. So now I've opened that line. So now you can see the this line is open and then the other line is getting loaded like this. So like this, you can change the status and do this. We call it as what if analysis. See now again it came back to 243. Similarly, you can open the transformer also. So this is one of the features which normally our team uses for various studies. So now I'll go back to, so I have to set back the simulation option. Now I'll go to the fault analysis. So here again, when it goes to the short circuit studies, so here you have to choose what is the kind of fault, whether it is three phase, single line to ground fault, double line to ground fault, and also we have the option to do open phase faults also. Okay, so I'm just choosing this, and these are the different options when you're performing the load flow, when you're performing the fault calculations, whether fault is on a bus, on a line, or on a traction load, and if the fault is on a bus, what are the selected buses, whether it is selected buses, voltage levels. Here in this case, it is a very small system, but when it comes to very large network, say you want to do analysis for all the 400 kV bus or 220 kV bus, you can select the voltage levels or the options. Now here we have selected bus 4 as the fault bus. And then for generators, what kind you want to use, transient or subtransient reactances. So these are different options here. So now I'm just going to say execute. So now whenever analysis is done, you get one as the textual report. So this is the report just now what we have executed. So it is a single line to ground fault at bus 4. You can see April 25th, just it is. So what are the fault levels? So 2789 breaker rating. So and also like here, one second, I'll go to this bus. Okay, so fault is at what bus? Bus 4. So it gives in the report, in the analysis report, all the sequence currents and also the phase currents. So this is a single line to ground fault. You can see here all the three phases are same, and then phase currents, and then you have the post fault bus voltages. You have from all the buses what is the post fault bus voltage, and also like fault contribution from the other elements. So these are the things which you can see in the report. So now I can plot the same thing on the single line right now. So plot. So here you see bus 4 have created the fault, and these are all the contributions from the various. Now there is one more option, like how we have the dynamic simulation. So I can select a bus here. Okay. So I can see right click and see fault simulation. So here, this is what I was talking about when I said in the beginning, you can use the computed or user given. When I say user given, I can tell at this bus what was the measured fault current. Okay. And then if it is fault on a line, so what is the fault distance that can be given, fault type, and this one. Because I've selected a fault on a bus, it is not giving me this option, a fault at a distance. Then what is the plot option? What is the type of faults? So now you see here the fault symbol moved here, and then it is showing me the fault. So similarly, you can create the fault at any of the points here, and then you can see like what is the fault levels. Okay. So that's about short circuit studies. Now we'll go to the relay coordination. So I'm just showing you once the network is drawn, how quickly you can do the different analysis. So here relay coordination, you have similar to short circuit study, some selections will be there, whether you compute the settings or verify the settings, and then whether the output graphs has to be generated. Okay, so the relay coordination. Now I'm going to do phase relay pairs. These are all the relay pairs that is available here. So I'm going to use automatic generation of relay pairs. See, protection as such is a very big topic. So now I'm just showing you once the data is there, how it can be executed. So if anything in particular you want to know, you can stop me or you can call me back also, because I'm just showing how to execute this and what are the results you're going to get. Okay, so here when we talk about relay coordination, it will be basically your graphs and just opening the graph. So this is the graph what you're going to get. So now I have plotted all the relays that is available in the thing. But what normally we do when we are doing the analysis is we take a particular limb and then plot only those curves. So Next is we have the distance relay coordination. I'll go to the stability. Okay. So transient stability. See, once I create the network and give the proper data for that, we can do all types of analysis. So when I go to the transient stability, so there are various options here. Okay. So what would be of interest is the different types of faults that can be simulated. So whenever we talk about transient stability, it is for a particular disturbance, right? You have a disturbance in the system, and you're going to observe how your system is going to behave, whether it is going to come back to normal or it is going to go out of synchronism. So these are the various faults that can be simulated. So it was like normally when we do for a large network, we even go for a no disturbance case, like where there is no system change, whether my system is stable. See, to check my validation of my AVRs, or governors, or generator parameters, we first run without any disturbance. There should not be any variations in the system. Next is change in transformer parameters. So if there is any change, like two circuits, it becomes one circuit, or if there is a change in the tap, those kind of changes can be done. Then change in transmission line parameters. It's again you want to open a line or a double circuit line, you want to make it as a single circuit. So those kind of data changes can be done. Then change in load, again load throw off or suddenly a load coming up on the system. So see here you are just modeling or telling, okay, these are the disturbances at these time intervals. It is going to at this time there is a disturbance. These kind of information can be given here. So the different types of faults are change in transformer parameters, transmission line, load data. Then you have this three-phase to ground fault, change in number of generator sets. So if there are four generator, it comes down to two. So what happens? How the system is going to behave? Then change in the complete generator outage, single line to ground fault. So these are the various disturbances that can be similar. Loss of excitation, change in shunt impedance, change in load model, motor. If you have a motor, so we don't have a separate study for motor static, so that is a part of this stability. And then you have the loss of turbine input. So these are the different disturbances that can be simulated. Even the single pole opening, two pole opening, then you have the wind farm outage. So this is for wind and solar park outage. So these are the different disturbances. Here in this case, I've created a three-phase to ground fault. We'll just see what it is. Three-phase to ground fault. Okay. So at bus 5, then start time, clearing time, and fault location. So because it is on a bus, there is no fault location field. Then you have fault impedance. So if it is fault is through a impedance, what is that? Fault impedance. And if it is a single line to ground fault, normally people would like to study about the reclosure analysis, like single pole reclose if it happens. So if any reclosure has to happen, this is you're defining the disturbance. And here, whether you want to consider AVR, governor, then the control blocks. So these are all the various options for doing the analysis. And even we have an interface with the phasor measuring unit also, PMU. So the analysis is done. So here you get various graphs. So you can observe the terminal voltage, whatever the selected. You have 1, 2, 3, 4 buses selected. So on that, if you, what are the options? What are the selection? So usually x-axis is time. Okay, y-axis I want to. So this is how it is going to. So I just plotted all the graphs. So like this, you can see whether it has come back to normal. Whether say if it is not coming back to normal in the graphs, you can observe like how it is going to go out of sync. Well, this is a voltage, but a frequency, a swing curve, all those things can be. So like this, you can perform various studies. I think I've just introduced what MyPoor is all about. I'm running out of time. It's already 4:57. Sorry for taking more time. So, but it's a very huge. I mean, what do you say? There is a lot of things. I've just given you a very small overview of this because it is around a 25 years product. Like you will have hundreds of features. Some like you can do all types. And one advantage with PRDC is we have a consulting division. Like it's not that we take something from the research and then implement that in the software. So we have a research R&D team also, but basically our inputs or what has to be there in the software comes from our consulting group who actually does or solve the real life problems. It is not like just it does have an impact on the actual field. So we go hand in hand, our power system consulting and software. So whatever development or whatever the inputs we get is from the power system community and also from our own consulting division because they face day to day issues like what has to be done, what should be the solution. Some of the times we do a lot of research and come out with an innovative solution which may not be a some published paper or anything, but we do publish our own how it is done, and that gets implemented in the field also. So like this you can do various studies. I mean this was just like 4 or 5 modules which I have shown. So if any particular module or anything in particular you want to know, you can get back to me or Sir Patil sir.
Yes,
So
ma'am.
yeah, no, anybody if they don't know my address or my number, you they can get in touch with you if they want any particular study or anything in detail if they want to know. So this
Yes,
was
madam.
just a brief about the software, and I'm very happy that this software is used for practical purpose also. It is
Yes,
not
yes,
only a
madam.
theoretical one where see when we studied, we used to think how this is useful or why we have to do this. But now I'm actually seeing what is the impact of that on the field. We simply say generator outage. It's when we are talking in terms of technically, we say okay, generator, but that has got so much of impact on the actual field. The other day we were discussing with one of the clients, the Reliance. So for them, the city saturation it happened, and they told they, like, the loss was around 5,000 crores. I mean, see, like small things. What from our domain side we feel okay, what is the city saturation, what happened. But when something of that sort happens, it has got a major impact. Like whatever we study, it has got, I mean, we may not understand at the level when we are a student, we may not understand, but there is a lot of impact on what we study, what we analyze, and what we give as a result to the what industries or utilities. So that's all from my side.
Thank you, madam. Thank you. It is a very nice session because we are also knowing because last 2 3 years before I have attended that session in Kolhapur. Whenever this is
Okay.
also at that time also it is online, but some modifications are done in that software. I think so.
Yeah, yeah,
So
it is a continuous development, sir.
yes, yes, ma'am. On the behalf of our SKNCU, Senior College of Engineering, Pandharpur, and our Honorable Principal, Dr. Kailash Karande, sir, and Vice Principal, Dr. S.G. Kulkarni, sir, and our HOD, Dr. Bhalchandra Godbole, sir, I really thank you very much, and it will be given us very good information, and I will definitely inculcate in the students regarding this software because we are having the power system 1, 2, and 3 in our curriculum, but
Okay.
basically there is no practical approach. So I want to introduce this my power software, and really it gives very good information to my students also. Thank you very much. Thank you, madam. Thank you.
Thank you, sir. Thank you all. If you have any queries or anything,
Yes, yes,
you
madam. Definitely.
can get back to me. Thanks for giving an opportunity.
Yes,
Thank
madam.
you. Thank you all.
Thank you.